makes me blue. Well, the music plays and you display your heart for me to see. I had a beer and now I hear you calling out for me. And I hope that I don't fall in love with you. Well, the room is crowded, people everywhere. And I wonder, should I offer you a chair? Well, if you sit down with this old clown, take that frown and break it before the evening's gone away, I think that we can make it. And I hope that I don't fall in love with you. Well, the night does funny things inside a man. These old tomcat feelings you don't understand. Well, I turn around to look at you, you light a cigarette. I wish I had the guts to bum one, but we've never met. And I hope that I don't fall in love with you. I can see that you are lonesome just like me. And it being late, you'd like some company. Well, I turn around to look at you, and you look back at me. The guy you're with, he's up and split the chair next to you's free. And I hope you don't fall in love with me. Now it's closing time. The music's fading out. Last coffee drinks, I'll have another stout. Well, I turn around to look at you, you know where to be found. Search the place for your lost face, 'cause I'll have another round. And I think that I just fell in love with you.
Welcome back. This is Computer Science 3, CSCE 310. And yesterday, originally I was going to go ahead and start the next topic of this course, the second to last topic, which is dynamic programming. But I decided that since we're doing so well, mostly because we picked up an extra day by having a take-home exam for the midterm, that we're a little bit ahead, actually. And so I thought, all right, well, since your homework is due tomorrow for graph algorithms and stuff, I decided let's go ahead and take a day and do something else. In fact, we're going to go ahead and do something related to graphs as a follow-up to what we've been doing. And I'm just going to go ahead and help you out maybe by doing some coding demos with respect to graphs and graph algorithms. If you have any questions or suggestions, I have not prepped complete programs here yet, so this will be a live coding demonstration. I can and probably will screw up. If anybody can go ahead and help me out on Piazza, please go ahead and engage on that live and Q&A, because I am not watching the Q&A on YouTube for bandwidth reasons. Okay, so let's go ahead and get started here. All right. I did prep a little bit here, but not any of the algorithms that I want to do. And let me go ahead and walk you through what I've already done. So first of all, I've chosen to use Network X, which is pretty standard Python library for graphs representation, graph algorithms. It's the one that I've suggested that you use as well. And as part of that, of course, the first step is making sure that you can parse the input files, which is not really the focus of this course. I mean, this is kind of like CS1 kind of stuff. So if you want to use this code, that's perfectly fine. And I would even be willing to post this later on if you really want it. But I defined this function here that parses a text file representation where the first line is n, the number of vertices, and each line is a space delimited triple. So it's a weighted undirected graph, just like in your assignment. And I think I've got an example here. Maybe I had an example. I'm not sure where it is anymore. Oh, I need to expand this. Sorry. So here's a weighted graph example that we've got 5 vertices. This is kind of like just a star where vertex 0 is connected to everything else. It's connected to 1 with a weight of 5. It's connected to 2 with a weight of 3, etc. So it's a pretty simple representation, and this function basically processes that file and creates that weighted graph. And now let's walk through a few of the lines. First of all, you just grab all the lines, and for the first one, I strip out all the white space and I get that n, and then I add all those nodes automatically using graph nx's add nodes from, and using the range, so it's 0 to n minus 1. Right. Then for each one of those lines, I split them out. I expect 3 tokens. If I don't have 3 tokens, for example, if it has trailing white space or something like that, then it'll get ignored. Of course, if it's malformed input, there are like 4 tokens or something like that, then, or 2 tokens, then it'll also be ignored. You're not expected to handle that kind of bad input. Then we add the edge, converting the first 2 tokens into integers, and then we use I think they call it an attribute. Over here, I've got the tutorial up here for GraphNX, or Network X, sorry, is what I think I've been calling it, GraphNX, but it's Network X. Let's see, weight, right? Yeah, the edges from, so you can use this syntax here to indicate the weight of, and I'm using a floating point number here, the weight of that edge going from this vertex to this vertex over here. And then we just make sure that it's undirected and return that out. So at this point, I'll go ahead and close that because we don't need it anymore. I import that over here, and then I'm just opening up like the second test case. These are the official test cases here, and that's what it looks like. The tutorial that I'm looking at here is this URL, and you can go ahead and follow along with that. Hopefully you've found that useful. I think I posted that as well. I'm visual, and so one of the reasons that we require you to make your own test cases is so that you have something to work with. And now the way that you design a test case is you just write it out on a piece of paper, a graph test case that is, and so that you have a visual representation of it. And then you can go ahead and simulate your algorithms on a piece of paper to understand how the algorithms work. And then ultimately, you have that produces a test case. Then you take that paper, pen and paper representation, you put it into the format that we're expecting for the assignment, and then you have a ready-made test case that if I ran DFS on this graph on this piece of paper, then I would expect this ordering. Right, so it's working from a piece of paper, a visual representation, into the abstract algorithms that you're actually going to be implementing. What I wanted to do, though, is I wanted to work the opposite way, and you might be doing this yourself. There are ways that, meaning that I wanted a visual representation of the graphs that are in our test case bed here. I think we've got, how many test cases do we have? We have 71 graphs or so that we've collected over the years. They're all simple graphs. They're not that big, but there's a wide variety of them. And I wanted a way to visualize that so that I could verify the algorithm that I'm going to write is actually correct, right? I didn't, and so I looked it up, and NetworkX does have a Matlab Matlab Plot, but of course it requires an installation of Matlab, whatever that is, and I wasn't willing to go that far, so I looked at some alternatives, and I found this guy's NetworkX to TXE. TXE is what I've recommended that you use for graph drawing if you're using LaTeX. It is a high learning curve, but LaTeX is a high learning curve, and that's why we're allowing you to make graph representation however you want to, including writing it by hand and then taking a scan or a picture of it, and that's fine. But I'm importing its plot tool that he has over here. This is part. I just pip installed this. It is part of the standard package, and it basically produces output that looks like this. This is just LaTeX TXE output. I also had to download his TXE network package, which is a LaTeX package. If you don't know anything about LaTeX, that's perfectly fine. And you can use this, but you should probably know a little bit about LaTeX and installing stuff and grabbing a style file. So let's go ahead and take a look at this input 2 here. Right? Then it's got 6 vertices. It's got 1, 2, 3, 4, 5, 6 edges here. What does it look like? Well, you can go ahead and manually go through this and draw it on a piece of paper here. But what I did is I simply just loaded it up from my own utility function here that loaded the file up. I printed out the edges. And let's go ahead and take a look at that. That was just a sanity check to make sure that everything worked. 0 to 1, weight of 3. Right? 0 to 1, weight of 3. The last one is 4 to 5 with a weight of 10, etc. Right? This right here is the internal representation in NetworkX itself. This is just a sanity check to make sure that it worked. And at that point, I can go ahead and get rid of that. Matlab Plot, again, it's going to be another install. So I just took maybe a half hour, an hour to read the documentation and for this network to TXE library. And I set up some basics here so that I could get the node labels, right? And here's something hopefully that you've picked up if you've been doing Python. This is a list comprehension. So G, which is my graph up here, has a list of nodes. I want all those nodes, but I want them as a string representation. So what I can do is for x in G nodes, I can go ahead and apply a function to that. In this case, I'm just converting it to a string. This produces a new list. And this is a list comprehension, kind of like set notation in mathematics. All x such that, and then you have the vertical line, x is even or something. Right? You can use list comprehensions. You can also use dictionary comprehensions for Python, and it's very, very convenient. Instead of writing your own loop and doing everything manually, you can go ahead and do it with comprehensions. This list curve, this edge curve, that's an option in the package that you can draw it curved, and we'll see that in here in a second. When I was playing around with it initially, the default random layout of the graph was kind of terrible. It just randomly put the nodes within a box and then drew the edges wherever they may be. So it was all a big spaghetti mess that you could not make heads or tails of. Fortunately, it has built in some graph drawing. There are lots of graph drawing algorithms out there. In fact, there's an entire conference for graph drawing, I believe, where I forget what it's called, but there's entire conferences on that topic itself. How to best draw a graph to minimize edge crossings or stuff like that. And there's this nice Fruchterman Rheingold algorithm that they implemented in this library. And so I just grabbed that, and it turned out to be much nicer. That did require some additional installs through pip. SciPy, I think, is a required package for that. And so I'm using that algorithm to render it. And then I wanted the edges labeled with the weight. So here's another list comprehension. the g.edges.data weight will give you a tuple representation of all of the edges. So the x, y, those are the two vertices that connect, and then the edge weight here, and I have to treat that as a triple because that's what this returns. And I'm not interested in x and y. I'm only interested in the weight here. So I'm grabbing that out and making again another list comprehension here. Okay. So let me go ahead and run this. Well, we already ran it over here. I can run it again if you want to. And it produces this mygraph.tex file, which again looks like something like this. I'm going to go ahead and typeset that and render it. It's already up here. But of course, the orientation is going to be randomized each time. But the Fruchterman-Reingold graph algorithm is going to make it look a little bit nicer. Those curves there, that's the 0.2. If I just left that at 0, then it would look more, I don't know. Let's take a look at what it looks like. Recompile the tech, and it looks something more like that. All right. So this gives me a nice visual representation of a graph that I can now work with. And now the real fun begins. Okay. So if you have anything specific that you'd like to see that, of course, is not your homework, let me know. But I decided that I would start out to let's write a function that, given a graph G and two vertices X and Y, and should we use X and Y? All right, let's go with A and B here. A and B outputs a path from A to B if, or outputs returns, right? Thinking pseudocode there, outputs a path from A to B if one exists, right? So we're not looking necessarily for the shortest path. We're not looking for the shortest weighted path. We're just looking for a path. Shortest path, shortest weighted path, that's your homework, right? So what I'm going to do is I'm going to adapt, let's adapt DFS to solve this problem, right? Depth first search. Let me go ahead and give myself some more room here. All right, so let's go ahead and define the function def, find path. And we'll take a graph G, let's go with lowercase a and b, right? One other thing that you should probably get into the habit of doing, I like two space indentations, but that's not the habit that I'm talking about. The habit I'm talking about here is documentation. If you've not gotten into the habit already from Computer Science 1 and 2 of automatically documenting everything that you do, you need to get into that good habit, right? Because writing is simply just documenting a function will actually let you determine, what am I actually doing here, right? Don't lose the forest for the trees. I kind of wrote it up here, but now let's be a little bit more formal about it. In fact, what I'm using here is, I believe, Python has not a pip, but a pep, I think, that governs documentation style. Python pep documentation style guide. Okay, pep 8. There it is. So documentation strings. You should be using this format here to document your functions, and that's what I've started here. That's a multi-line comment basically, and we'll go ahead and say what this function does. This function finds a path in the graph G from the vertex A to the vertex B if one exists. No conditions, shortest distance or weighted path are placed on the resulting path. Right? Returns none if no such path exists. Right? And this is not rendering correct because I didn't put my colon there. But now it renders correctly. Otherwise, it was treating everything as a keyword inside that stuff. Okay? So let's remember what our stack-based DFS looks like. Here it is. Zoom in a little bit, right? That we're going to use these colors to indicate whether or not we've visited something. We can also keep track of the counters. I'm going to go ahead and get rid of the cruft. We're not going to use anything that's not absolutely necessary. And so the initial discovery times, because I'm adapting DFS, so the discovery times and the finishing timestamps, they're not relevant to what I'm trying to do, so I'm not going to keep track of them. So I'm not going to keep track of the counter, but I do need to keep track of the color in some sort of conceptual way to make sure that I am not backtracking. If I were over here in this graph and I started at 0 and I went all the way around this cycle here, came back to 0 and never discovered 1, I need to know that I'm not going to get caught in this cycle here. I need to know that it's going to terminate. So I will keep track of the color of the vertex, but I'll do so separate from the vertices themselves. I'll just maintain a map, a dictionary, and keywords, or just as strings. So what I mean by that is, let's go ahead and create a status, and it's going to be a simple dictionary, a mapping. And we're going to map, and I wouldn't normally put this in as documentation, but since it's a demonstration, I'm going to go ahead and put it in. Maps vertices to strings for the status for their status. All right, I'll go down to the next line here, including unvisited, right, or visited or processed. And then I can just check those string values. Off the top of my head, I forget if Python has enumerated types, but you could use that as well. Yep, support for enum types. And you can create you have to import it, it looks like. It's not part of the standard language. Weird. Yeah. So you could do something like this instead, where you defined these things. I'm not going to do that. This will work just as well. You could define it in line here if you really wanted to. And so I'm going to go ahead and initialize here. For every vertex, I'm going to color it white, but instead of coloring it white, I'm giving it more meaningful expression of its status is unvisited. So for x in g.nodes, right? Status of x is going to be equal to unvisited. Right. There we go. Okay. You should probably be consistent about your indentation. So my editor is not pulling up the indentations here that I prefer, just space. It's going to full tab over. So maybe it'll learn if I do it like that. Okay. We're also going to need a stack, right? An empty stack. There is no stack that's called a stack in Python. Hopefully you've picked out that you can use a list instead. So I'll just call it what my stack is S, right? And so this is my stack. All right. Remember that you can push things or pop, but in Python there is no push. Pushing at one end, at the other, at the end of the list is simply just append, and popping is popping off the end. Okay, so you have those available to you. In fact, what we're going to do initially is we're going to visit that initial vertex A. All right, so we're going to go ahead and go s.append A, and we need to change its color because it's now visited. So status of S is equal to visited. Right. And by the way, you might have done most of the homework already in your own style or in completely different from me, and that's perfectly fine. You don't have to go back and redo everything in the style that I'm doing it. If it works, it works. You're not being judged on or assessed, at least. You are always being judged on style and efficiency, but you're not being assessed on it as far as your grade goes. Okay? It just has to work. Excuse me. All right, still no questions or suggestions. So let's go ahead and continue. Now I'm going to go ahead and start the DFS here. I've colored it gray. Again, I'm just using that it's been visited, but not processed yet. Remember, this is white, gray, and then black. But using the actual words is much cleaner and much more communicative, that you can easily understand what's going on. All right. Good question here. Remember you mentioning that there was a dictionary comprehension, and assuming it works like a list comprehension, could you initialize the status dictionary to unvisited in one line using the dictionary comprehension? It's a good question. Good digression. I'm going to have to remember the syntax for Python dictionary comprehension. Okay, thank you for correcting my spelling. You understood what I wanted. Let's see. Where would be an example? Comprehension. What do I want? Yeah. I want a full comprehension here. There we go. That'll work. So let's go ahead and try it, I guess. Dictionary key, so in this case it would be status instead. And this is what we want, the key value pair. So the key here would be X unvisited for key I'll go ahead and go with X here. X in G dot nodes. There we go. All right. Okay. Let's go ahead and test that out. 1, 2. There we go. All right, and let's print it out. Print status of 1. I don't have a proper debugger. I'm just using Atom.io here. So great question. Let's find out. Oh, and then I guess I need to invoke this. So down here, we'll go ahead and find the path from, I don't know. We know that there's one from 1 to 5. There's a path from everything to everything. 1 to 5 in the graph G, and the G is up here. All right. So again, we're not finding it yet. I'm just seeing if this list comprehension or this dictionary comprehension works. Oops, there we go. That's bad syntax. All right. Pull this up here. That's the first one. That's the second one okay, probably because I should print it, of course, afterwards, but I already have my answer here that worked nice, right? 0 unvisited, 1 unvisited. So yes, I absolutely agree that we should go ahead and that's called doing it the Pythonic way. Using comprehensions is preferred over writing your own loops. It's more functional style, and Python folks call it the Pythonic way. Okay. And status is undefined, so now I'll go ahead and restore it. There we go. Excellent suggestion. Keep it up on Piazza there. So again, let me walk you through this. This is a dictionary comprehension. I'm establishing a dictionary because of the curly brackets. This is a key value pair here. I'm going to map vertices to the string unvisited. Of course, you can change the key as well, but because I wanted to set them all to the same thing, I'm just hard coding this unvisited right here. And then I'm doing this for each X in G.nodes. So this basically is my loop here, and it's an enhanced for loop, a for each loop, basically. X in this collection right here, which happens to be, I believe, a list of integers, the way that it's set up for a network X. And then now each one of those becomes my key, and each one maps to unvisited, giving you this thing right here. All right? Excellent idea. I like it. All right, so let's go ahead and continue here with our while loop. So while the stack is not empty, right? While S is not empty, And it's just a regular old list, so I'm just going to have the length is greater than 0. Right? Then we've got other values to process. So what I'm going to do is I'm going to look at where I am. I need to peek at it. Well, there is no peek function because it's not really a stack. Semantically, it's not a stack, but in practice, we can treat it like a stack. So I'm just going to peek. The way that I'm going to do that is I'm going to say, what is my current vertex? Well, it's whatever is at the end of my list, at the top of my stack. So S, and then the last one, you can use this syntax in Python to get the last one. Of course, this 0 would be the first one, second one, third one. The last one would be length of S minus 1. Well, okay, why do that when you can just go minus 1? Right? A trick if you didn't know about it. Okay. All right. So that's the current vertex. What I need to do now is choose the next vertex that I need to go to. Remember, depth first search. I'm going to go as deep in the graph as possible before I start backtracking. So I need to select the next vertex to visit. ... But before I do that, let's remind ourselves, what am I trying to do again? I'm trying to see if A can be reached, can go to B, right? I'm starting over here at, say, 1, and I've traversed, done a DFS over to 0, to 2, to 5, and if 5 is the thing I'm searching for, then I'm done, right? Why search anymore? Right? So I need to see if the current vertex, where I am, is that the thing I'm looking for, right? So check if you've found B, right? If current is equal to B, then I've found what I'm looking for. And I can stop and I can return. Right? Return the path that led me here. Right? So obviously that's not real code. So how do I know what the path that led me here is? Remember, you have a stack, right? Your stack are your breadcrumbs. So if I do a depth first search and I go from 1 to 0 to 2 to 5, guess what's in the stack? At the top of it is 5, 2, 0, and then 1 is at the bottom because that's where I began. So if I find what I'm looking for, stop and return S. Right? That's your path. Right? Else, then continue on, but I'm not going to put that into an else statement because I'll just return. That's perfectly fine to continue. Right? Otherwise, I need to select the next node to visit. Right? That's going to be in the current node's neighborhood. Right? And so let's go back to the tutorial here. I forget off the top of my head. Neighbors, I think it is. There we go. Right. So g.neighbors. And if you give it an actual vertex, then it's the same as going by g.adjacent, but if you treat that as a map or a list or something like that, but you can get the list of neighbors because I want to iterate over them basically. So for y in g.neighbors of the current vertex, I need to find one that's not visited yet. So if the status of y, right, if its color is white over here in my the next white vertex in the neighborhood. So if the color is white, but I'm not using that anymore, I'm using unvisited, right? Then that's a candidate. And here's where you, in your homework, you would put, well, here's all the unvisited vertices. I want the lexicographically next one, right? And I'm probably getting that here, but I'm not sure. You'd want to dump this maybe to a list and sort it by lexicographic ordering. Otherwise, if your criteria is the next least weighted one, then you could dump that to a list, and you could even use a list comprehension there. Right? Explore how to do that on your own though. So if the status is unvisited, then I can go to it. Next is equal to y, and I'm just going to break out here. So I'm going to need the concept of next up here. So next is equal to none. It is potentially none because if I get to a dead end, right, and there's no unvisited vertices in the neighborhood, I need to start backtracking. So I need to check for that now, right? In fact, that's what we do over here in the pseudocode. If y is nil, then the neighborhood of x has been exhausted. I need to start backtracking. Otherwise, I will visit it by coloring it gray, marking it with the discovery time, which we're not doing, and pushing it on the stack and exploring its neighborhood next. Okay? So if y is, we'll go in the same order, none, right? Then we are done exploring this corridor or this route, done with current need to backtrack. Right? Oh, sorry, if not y, next. There we go. Okay. So we need to backtrack, else, colons. There we go. So we're done. We need to backtrack. And that means just simply that you're going to pop it off, process it if you need to, color it black, in other words, that it's been processed, and then move on. I'm not doing the processing time. I'm not actually even processing it because the real work for this algorithm is right here. If you ever find the thing that you're looking for, stop. That's it. Go back. Right? You're done. Right? And return. So all we need to do is pop it off, s.pop, right? And of course, not s, s.pop. And we can capture that, but that's going to be equal to current already. So update the status of current to be processed. There we go. Otherwise, we explore, we go to next. We go to the next vertex. And all we're doing there is pushing it, coloring it, or in this case, changing its status. Status of current is equal to visited. And we'll push, so s.append current. There. That's the end of the while loop. Right? If we get done with everything and we never find the thing that we're looking for, I'll just simply return none. Right? And that'll be our flag value to indicate that there is no connection from this vertex to that vertex over there. Okay? Let's go ahead and try it again and see if this works now. Oops. Just syntax errors. Where is that? There we go. Thank you, Python. Oh, no. Unhashable type list. Oh, darn it. Let's see. Line 40. Visited. Ah. Okay. Oh. Not the status of the stack. The status of the vertex. There we go. That was line 40. So we've got some sort of infinite loop here because no way is it going to take that long. All right. Where were we stuck? Line 48, it looks like. All right. Okay. If status. Let me know if you see any the issue here. But otherwise, if status of y is unvisited, then next is equal to y and we break out of the loop. I don't see a problem with that at all. Current is going to be peak. If current is equal to b, then we go. Otherwise, okay. All right, time for some poor man's debugging unless anybody sees what's wrong. Print current current is equal to str current. And we'll definitely see that we're stuck in an input loop here at 1. So it looks like we never got out of 1. Right. For y, and okay, here. You use current instead of next in the else statement at the end. Oh, thank you. So go to the next vertex, and then we were pushing current. We were pushing 1 over and over and over again. Thank you. You chose to remain anonymous, so I won't say your name. But shout out to the anonymous helper on Piazza. All right. There we go. So 0, 1, 2. Okay, we could get rid of that poor man's debugger now. And I'll just go ahead and comment it out for now. All right. So let's capture that path. Of course, that's not telling us how we got there, but at least it terminates now. Great. Print P. Right. And let's see. There. So 1, 2, or 1, 0, 2, 5. Looks like it works. And it did, in fact, go to the lexicographically least one next by default. If you wanted to go to the next least weighted one, you'd have to, of course, change that. Let's go ahead. That's not enough testing, though. We know that everything is connected in this graph because of the visualization here. So let's make sure that everything is connected. For I in range from 0 up to, let's see, 6. Up to 5 because it goes 1 less. For j in range from I plus 1 or I plus 1 up to 6, then I will go ahead and find all of the paths and print them out. And then we can just spot check this by just writing these simple code here. We can spot check these. It might help to go with I to j because those are all the same paths, and then I going to j equals path. Stringify these. There we go. All right. That's good. 0 goes to 1, 0, 1. 0 goes to 2, 0, 2. Those are kind of uninteresting. What about 0 to 3? 0 goes to 3. That's nice. It just didn't go to it. We didn't put any conditions on it. So it actually went all the way around over here. It went to 2, 5, 4, and then back to 3. 0 goes to 4, 0, 2, 5, 4, right? Et cetera, et cetera. 4 to 5, another one where it could have just gone, and it didn't, and it just goes from 4 to 3 to 0 to 2, and then back to 5. So again, we weren't finding the most efficient path. We were just finding a path, right? And none of them return none. Let's test that, though. We should try to test that. Let's see, which one are we opening up again? Let's go ahead and open up the input here. What I'm going to do is I'm going to add one more vertex, but it's isolated, right? All right, there. Now I was able to save that. And what I'm going to do is I'm going to run this again. We'll come back over here. Typeset this. And well, there's that Rheingold, whatever, Fruchterman algorithm at work there. It's putting that isolated vertex, is really isolating it over here by putting it really far away. But you see that there's no path over here. And I need to make sure that I check that by not going up to 6, but going up to 7 on this. And we'll run that one more time and see that hopefully it'll print out none. Oh, okay. Save this. 0 to 5, 0 to 5. Weird. Oh, did I not go? Okay, I just retyped 6, I think. Duh. All right, there we go. So 4 to 6, none. 5 to 6, none. Anything that goes to 6, there's not going to be any path. So we took care of that as well. All right, cool. I'm going to take a break, maybe a 30-second break here, and come back. And if you want to see something else, we can go ahead and try something on the fly, maybe building a BFS tree or something like that. But if you want to see something else, put it on Piazza, and we'll try to do it with the remaining time that we have. All right, so I haven't seen anybody make a post yet. We are on a 10-second delay here. Oh, there we go. Here we go. Either a BFS tree or shortest cycle detections. Shortest cycle detections. You do have to write. I think that's in your homework. You have to write it only as pseudocode, though. The hint that I'll give you on that is the hint is built into the exercise itself. So finding the shortest cycle so that you can compute, I think, the girth or something like that, it can be done by an adaptation of the shortest path algorithm, which I'm not going to do because that's part of your assignment, and it's pretty easy to do anyway, choosing either Dijkstra's or Floyd-Varshall's. But the trick there is, as hinted in the first part, is here's a particular edge, right? Now, what if we were to take that edge out, okay? And then run a shortest distance or shortest path algorithm on it between A and B, right? That would give us another path that doesn't involve this edge right here, right? Visually, let me go ahead and bring up, if you want to visualize it, I can bring up like GoodNotes or something. But that's the idea. If you find the shortest path from A to B that doesn't involve this edge, and then you put that edge back, that's necessarily going to be a shortest cycle that involves that edge. And there's the hint that I'll give you on that exercise. But otherwise, maybe a BFS tree, okay. Here, minimum spanning tree versus a forest. Just a quick question. I still don't understand what the difference is. Can you explain what this means, please? Okay, I'm going to go ahead and bring up, oops, not that. GoodNotes. Didn't expect to be drawing today. So let me go ahead and create a new page here. So what's the difference between a minimum spanning tree and a spanning forest? Well, here's a graph, right? It has, say, 7 vertices. And now let's connect them like this. There. That's a disconnected graph. I mean, it looks like two graphs, but we're treating this as one graph, right? The vertex set are all 7 of these vertices. The edge set are these 1, 2, 3, 4, 5, 6, 7, 8 edges, right? Now, what if I were to do a minimum spanning tree? We'll just say that all the edge weights are uniform. They're all 1. So it doesn't matter what order we go in. I just need to build a tree with crucicles or prims. Suppose that we built a minimum spanning tree starting at this edge over here. I'll increase. There we go. We'll take that edge. We'll take that edge. We can't take this edge because that would induce a cycle. So we won't do that. And then we'll go ahead and say, oh, I'll take this edge. There we go. And then I don't take this edge because that would induce a cycle. Right? If I stopped there, I only have a tree, a spanning tree on one part of the graph, on one connected component of the graph. So what I need to do is I need to restart my algorithm, or it depends on which algorithm you use. If you continue using crucicles, then you don't need to restart because it'll consider all the other edges. It'll start considering these 3 edges over here, right? And then it'll take this edge and maybe this edge, just as an example. And then not this edge because that would induce a cycle, right? But the key there is that you don't want the stopping condition. Necessarily, this is going to be 1, 2, 3, 4, 5, 6, 7 vertices. So a spanning tree would end up having 6 edges. This one only has 1, 2, 3, 4, 5 edges, right? Because it is disconnected. So a minimum, you could end up with crucicles producing a minimum spanning forest. If you used prims, then you definitely have to start over, because if you just explore this over here, you'll never end up exploring this over here. So you either have to adapt it or change the termination condition so that you can continue over here. And now this is a minimum spanning forest. If you have a graph with different connected components, then you'll end up with 2 trees, right? And 2 trees don't make a forest, but in graph theory they do. Okay. Any other questions? No? Okay. All right. You're going to have to help me with this. Let's go ahead and get rid of this. BFS tree? I don't know. Maybe that's doing too much for you, since you'd end up doing BFS. No. You'd still have to adapt it because I think that it requires a particular order. So it's not that big of a deal to go ahead and go through this. First of all, let me go ahead and track through and find the pseudocode for BFS so that we can go ahead and use it as a reference. All right, so what I'm going to do is I'm going to make BFS tree. Build BFS tree of G, right? And if you want to, we can go ahead and have an initial vertex A. I'll go ahead and use the same variable as up there, right? So what is this going to do? This 1, 2. There we go. All right. So this function returns a BFS tree resulting from one BFS. I'm only going to do one BFS. Again, we have the same problem that if it's a disconnected graph here, a BFS might end up doing almost exactly would end up producing a BFS forest rather than a minimum spanning rather than a BFS tree. And so I'm only going to show you the one way. I'm not going to. It's a pretty easy extension to just start over and produce a forest. But what I'm going to do is I'm going to return a BFS tree resulting from one BFS starting or run iteration starting at vertex A. Right? Okay. So that means I need a new graph, right? That's going to be my BFS tree. Okay. And how did we instantiate a graph? It's just graph, I think. nx.graph. Right. And it'll have, there might be a copy constructor somewhere, but we can go ahead and just say that it's going to be the, let's see, where's my utils? All right. It's going to be something like this. So g.nx, okay, nx.graph, I've got that. And then t dot add nodes, and then in the range of what's n, I need t dot, or length of g dot nodes. There we go. So I've added all of the edges so that I know that they're there. All of the vertices so that I know that they're there. But I have not yet produced the actual edges that constitute the BFS tree, because I need to write the BFS. All right, so let's go ahead and do that. I'm not going to keep track of the count. I'm not going to keep track of the discovery time. I do need to keep track of the status, whether or not you've seen this before or not. And I'm going to have a queue. All right, Q is equal to. Ooh, that's a good question. How best to use a queue in Python? We could probably go ahead and abuse a regular old list. I don't need a synchronized queue class. Oh, there's a deck, it looks like. Here's a demonstration. Okay, fine. Well, Geeks for Geeks, I would expect that from you. They're abusing a list here, it looks like. Fine, we'll go ahead and abuse a list. But I want to give you a warning here, because some people were doing this on their first assignment. So this is going to be our queue. And DQ is going to end up being pop from the first part, from the index 0. So popping off the front is going to be dequeuing. Enqueuing will then just simply be append. Right. So we're going to add it to the end, pop it off from this other end, and that will basically give us the behavior of a queue, FIFO order, first in, first out. I very much hesitate to do this, because I believe that this is just an array list. And so if you do this at the front, it shifts everything down, and the DQ ends up being an order n operation. I'd have to look up the documentation to be absolutely sure on that, but it would be much better if you'd had some sort of a linked list implementation of this instead. And it's not telling me... Oh, here. I should have just been more patient. There's a deck. Pop left, pop right, append. Okay. Yeah. Thank you, Geeks for giving a better QPython can be implemented in a deck. There we go. For append op compared to the list, exactly what I was worried about. It's going to be order n time complexity. So let's go ahead and take care of that. I will use a deck instead. Deck. Oh, what was it? Yep, a new deck. And this will be pop left and append. Right, there we go. Much better implementation. Remember, an array list, if you're doing stuff at an arbitrary vertex instead of just at the end, then you're shifting things around, which is going to be an order n operation. All right, good. This should have been your first answer, by the way, Geeks for Geeks. All right. So we'll go ahead and start with A. I will do my same status, so I'm just going to steal the code that I had up here. That excellent list comprehension there. And I'll start with A. So the A status of A will be visited. Some people like to intermix, sometimes using single quotes, sometimes using double quotes. I prefer personally to use double quotes, but whatever you're going to do, make sure that you're consistent about it. Visited, and then we'll enqueue. So q dot append a. There we go. So I've started out by enqueuing my initial vertex. While Q is not empty, then I'll dequeue it, and then I'll look at its neighborhood, and as long as its neighbors are unvisited, then I will go ahead and visit them and then put them in the queue. Okay. So let's see. Let's move this over so I can reference it. So while the length of Q is greater than 1, right? 0, excuse me, then I will go ahead and in the pseudocode I'm calling it X. I'm going to call it current, just like I was doing up above, and just so that that's a much better variable name. Current is equal to Q dot, and it was pop left. There we go. And for each element in the neighborhood, again, I'm just going to steal this over here. For X in the neighborhood of the current, if it's unvisited, then I will go ahead and visit and queue it up in the queue. All right, and the way that I do that is status of Y is now equal to visited, double quotes, and I will enqueue, so q dot append Y. And I'm not breaking out of this because I'm not finding a neighbor. I'm going to all the neighbors, and I'm putting them all in the queue. So I colored it. I'm ignoring the discovery timestamps, etc., etc. Otherwise, then I'm done with current, or X, in the pseudocode. So mark X with count. Don't care. Status of Q X current is now equal to processed, right? And then I process it and process current and color it black. I've already done that. I already took it out of the Q2 up here. So this is where we're actually going to build our BFS tree. Okay. Actually, no. I don't need to I don't want to process it here. I don't want to know where I came from, right? So I'm at the current, and then every time I put something into the queue, because it's unvisited, that constitutes a tree edge in my BFS tree. So if it's unvisited and I'm visiting it and I'm putting it in the queue, I'm also going to add the edge from current to Y to the BFS tree. And the way that I'm just going to do that is, how do we add edges again? Add edge, oh, there you go. Well, I want this version. I want add edge of this. This is just for my utilities that's reading it from a file. I'm just going to steal that code and adapt it. And I don't want to add it to G. I want to add it to the tree. I will add it from current to Y with a weight of, not from the tokens, but I need to get the weight from the original edge. So I need to ask G dot, how do I get the weight? Let's see, find weight. That'll do it like that. Okay, looks like I can use this syntax right here. G sub current to Y and the weight. Right. There. And then at the end, I need to make sure that I'm indenting correctly. That looks like it's aligned. I'll return T. Right. T is equal to BFS tree on G, and where should we start? I don't want that anymore. Let's go ahead and go back and fix that. I don't want that isolated vertex, so let's go ahead and fix that to 6. There we go. There. And we'll start at, I don't know, let's start at 0. And then I'm going to print that out to another file using the same styling. My graph, my tree instead. And let's go ahead and run this and see if it works. Okay. Syntax error. Oh, okay. I might have gotten it on the first try here. I'm going to have to pull that up though. First of all, we can go ahead and recompile this to make sure that I took out that isolated vertex. Looks like that's okay. I'm going to have to navigate to where I am and pull up the tree. So there's the LaTeX for the tree. Go ahead and see what that looks like. And it's over here. There. So that was starting at 0. 0, of course, would have explored 1, 3, and 2. And then off of 3, we got 4. And 3 was not connected to 5, but off of 2, we got 5. That looks like a BFS tree to me. Right? You know what? Since I'm here, it just does a last thing since we won't go much. Let me go ahead and look at inputs here that we have. And let me select the most complicated or the largest graph. Looks like 26 is to be our largest graph over here. So let's go ahead and use that one. There, oops. And we'll do the same thing. All right, that worked. Here's my graph. This looked like an absolute mess when I first tried. Okay, it is going to look like an absolute mess here. Great. That's what the original graph looks like. Do I at least get a tree out of that? Looks like it. In fact, I even like this because it kind of it's kind of drawing it radially instead of hierarchical, like a tree. It shows you how BFS actually works. It starts at 0 and then works radially out here. It visits 1, 2, 3, 4, 5, and 6, and 1, 2, 3, 4, 5, and 6. Right, and then from there it visits the next radial out for each one of these things. And so it looks like it builds this like starburst coming out if you want to look at it that way. Right? Cool. Any questions? No? All right, then good luck with the rest of your homework for tomorrow. Tomorrow we will start. Oops. Now I'm dropping frames here. Tomorrow we will start with dynamic programming. Okay.